All right, good evening, everybody. I want to welcome everyone to the preview session. On behalf of myself and my co-chair, Ranjita Bhagwan, who unfortunately cannot actually make it to NSDI this year due to a personal kind of emergency. Welcome to the 2020 preview sessions. So the purpose, just to give you a very brief history, about 5-6 years ago, I think some of our conferences kind of in the SIGCOMM world and in the NSDI world have started this tradition of doing a series of preview talks to kind of give those of you that are maybe new to the community or that aren't super familiar with some of the sub areas that we're going to be presenting on, a little bit of context and background. And I want to point out that these sessions are actually recorded. And so I think it's still really valuable to have them so that they're part of our online record, et cetera. So we've got several experts who have graciously agreed to present on a variety of topics that you're going to be seeing over the next 3 days. And I will sort of mention that although they're going to be presenting some material, I believe if you have questions, comments, if something is confusing, feel free to raise your hand and we can make it a little bit interactive. Okay, so with that, maybe I'll turn it over to Brent, who can get us started talking about network stacks, RDMA, and protocols. And we just have to push the button. Great. I can take all the time you need.
Okay, thank you for having me. I'll make sure to speak into the microphone. Fantastically excited to be lecturing for a recording. I think it's very fantastic. Every student I talk to in my classes watches these things, so I think this is fantastic. I can't wait to be here for fun. I have a lot of slides. We might as well move fast. This is going to be an exciting talk, and by that definition, I'm going to go through a lot of slides. Very exciting. Okay, we're talking about network stacks. We have a brief overview. There we go. We're going to talk about what a network stack does, what are the different types of network stacks. We're going to talk about where you implement the network stack, and there's a few talks that I think we were going to point out specific paper background about what you should do in the control plane, how you optimize performance, how you do programmable packet scheduling. Okay, what are the different network layers? I've been teaching networking, introduction to networking this semester. This feels very familiar. We're going to go over this quickly. I don't like the OSI 7-layer model, so we're going to break it down to the 4-layer model. We have a physical layer, a network layer, a transport application. At the top, we have applications that are typically needing low latency RPCs, high throughput, and there's needs for cooperative scheduling. And general programmable ability. A thing we're going to skip or get to later is the need for high throughput, but getting that sort of cross all of these layers. Below that, we have congestion control. And one of the biggest problems that we have related to all of this is that we're still sort of undecided. There are a lot of currently active congestion control development, and there's sort of this mismatch between hardware devices being hardwired and not being able to implement the state of the art in congestion control. And also this need for sort of low latency. Congestion is occurring on such small time scales that sort of current stacks are not able to react or operate in time. Below that, we have the networking layer. We're going to talk about things like programmable scheduling and load balancing, about needing to scale out infrastructure. And I almost left this out, and I'm glad I didn't. Even the data plane is programmable these days. We have patch panels at the layer 1 that are really providing programmable topologies. These things related to optical networking really are very related to these layer 1 physical programmable. So if there's a takeaway here, if we're all familiar with this, is that there's a trend, there's programmability all the way through all of this. And so that's really what we're going to talk about for the rest of this talk. It says I've been started for 20 minutes. That's not true. We've been up for 5, so we're going to base it off of that. Okay, so what are the components of the networking stack? Where are we implementing this? This is a good overview of programmable storage, CPU, memory, networking, NIC, at least as I see it. Memory is the important interface here. So what we have, if we're trying to do networking, we're at NSDI, but we have some things with NVMe. We can't ignore storage. But it starts with a core, initiating communication. We go to memory, we go to a NIC, we go across a network, we go to the NIC back to memory, and then if we're going to storage, the core will initiate, we'll go to the storage. We have a talk here about RDMA over NVMe. So with this, your NIC will go straight to storage. We're going to talk about things like kernel bypass. And again, a big trend for everyone to make note of here is that everything is programmable all the way through. Okay, so starting with where do we map our network layers onto, we're going to go with inside the network. So we have a software-defined networking stack. I'm not sure if everyone is familiar with this. Hopefully they are with now, but there's this big separation of we run control plane algorithms in some sort of distributed software control plane. We're going to compile this down to and run it on a programmable data plane. Inside of host networking, we have things that are very, again, similar, but there's now sort of 3 layers, maybe 2, depending on how you're doing it. We have traditional operating system networking. We have an application layer going to an operating stack down to a NIC and network interface card. This is the thing I am excited about because it's what I do research in, but it is really your interface between Ethernet wires and PCIe connectors into the NIC. It's your first and last hop. So we have traditional network interfaces, kernel bypass, we just throw away the network entirely. There's things like Google Snap that sort of some way look like a traditional OS networking stack, but now it's like a library operating system and operating in user space. Okay, so I wasn't sure exactly what to talk about. I only have probably 5 or so minutes left, but the big question I think that we're asking in this conference as a whole is how do we map these different protocols onto these different layers? And our traditional mapping inside of the, before we're going to that, we're going to the software-defined networking stack. There's a big trend is all the layers inside the data plane, all the layers inside the control plane. There's a big push for programmability, but this is really needed for high-speed transport. So I guess this is my interpretation of mapping layers and protocols into the network. But there's sort of this big trend that we're going to come back to about this division of control plane and data plane. Really, all of the layers are present in both. So we're going to come all the way with transport application layer and all sorts of things assisted by the data plane, but also made scalable by the control plane. Okay, moving on. Inside the host networking stack, we typically divide up our layers among the stacks like this. Okay, application layer, there's lots of things with custom logic there. Custom transport control isn't available in the operating system network layer. We still have routing, things like RSS, segmentation, offload. These are typically done inside the OS, but they're getting pushed inside the NIC. And this is the trend of where we're going to next. This layer doesn't perform well, it's inflexible. We can look at Google. Packet line rates are increasing exponentially. Ethernet standards are increasing exponentially. We have 100 gigabit Ethernet, but 400 gigabit Ethernet is standardized, available running our WAN, and it's going to be available everywhere soon. This is problematic because we only have hundreds of nanoseconds per packet. And in general, we want low latency, high bandwidth, high throughput, low CPU utilization, and we're not getting this from today's networking stacks. Okay, so moving on, one of the big things that was a title and the thing we're talking about was RDMA and how it related to networking stacks. So my loose interpretation of this is we're now going to talk about how we're overcoming some of these issues I talked about with RDMA and wrapping up with hopefully enough time and attention. Okay, at a high level, this is an overview of kernel bypass networking. While we typically had applications interfacing the operating system, which is using multiple cores and managing different queues, we instead now have applications directly mapping for NIC resources. Okay, in DPDK-like kernel bypass networking stacks, we take our 4 layers and we push the first 3 into software. We onload them, and this is still much higher performance than we typically get out of today's operating system stacks. With RDMA, which we're going to talk about in a very brief flash fashion, we do the opposite. We offload the 3 layers that we see into the NIC, and we take the application, we have to modify it so that it's able to use these new hardware offload resources. Okay, we're going to talk briefly about DPDK versus RDMA. DPDK is very flexible. RDMA is not. Because RDMA has flexibility issues, this causes lots of problems with practical large-scale implementations. RDMA, because it has maybe concessions made for hardware implementations in the transport layer, typically requires lossless networking and is going to have maybe less performant and extreme sort of performance variabilities, especially if NIC state is blown out of and sort of transparently ignored by applications. They're just going to see a performance cliff. Okay, hopefully I'm not having microphone problems. Okay, but so why do we talk about RDMA? We're going to get to it briefly. This is because it can provide zero-pass sort of direct network interface performance. Okay, and one of these papers we're going to see, however, is that this is not necessarily going to inherently improve performance. With good operating system techniques, we can get near this sort of performance in practice. Okay, why are we going to RDMA? It's because one of the reasons here is it provides one-sided networking. Okay, what we see here now with one-sided networking is we have machine A access memory on machine B, bypassing the remote CPU. So it initiates a request from the CPU on machine B, skips the CPU entirely on machine B. This can provide predictable performance without requiring dedicated CPU resources. Okay. The NIC, however, is a coprocessor, and that is going to lead to some limitations that we're talking about. We're going to see not one but 2 papers that are having to work within these coprocessor limitations of Smartnics as accelerators. Briefly, for RDMA, we have to have a new interface. We are bringing it up here. It introduces reads, writes, and types of reliable and unreliable connections, but importantly, everything is centered around queues. Reliable connections are what we're mostly going to talk about. They can provide congestion control as well as reliability. With verbs, these 2 ping-pong diagrams are very helpful for illustrating how the CPU, memory, NIC are involved. We can read memory. This is one-sided. We read memory without involving the remote CPU. We write memory as well without involving the remote CPU. There's a big sort of active area of discussion about whether we need to use polling or interrupts inside our applications. There's a big trade-off here, but in general, we're going to see a lot of systems that use polling for high-performance networking. This is because it can be fast in its response to receive data, and we're willing to waste and burn CPU resources for ultra-low latency. Interrupts, however, are still an option. Another big option for RDMA, as we're wrapping up our conversation with this, is how do you use it to build applications? So in this example, we have a hash table that requires 2 memory accesses to walk your hash table and find your object. To do this, you can either use 2 reads, which you go across the network twice, or you can use a compound read, where you go across the network once, but you involve the remote CPU, while our initial read didn't. So these are big trade-offs for RDMA. We're wrapping up here. Hopefully I'm not taking too long. But so briefly, we're talking about control plane versus data plane offloading. We're talking about layers and where do we implement them. And really, one of the things that we're going to come to in a lot of these talks is that you don't necessarily want a clean separation of these layers between your data plane and control plane. You want fully programmable layers of the networking stack on one side to be sort of programmable from software, but you want them to be implemented very fast in the data plane. Okay. We're going to talk about optimizations. There's a paper here about NVMe over RDMA versus the TCP stack. So one of the things that we're going to see is that from the CPU side, if we use large segments or batching, or if we scale out performance by giving each CPU its dedicated resources that it can operate in parallel, we can significantly improve performance. Okay. And finally, we're here to the last paper-specific general overview in the talk. And this is for programmable packet scheduling. So the state-of-the-art that I'm hoping that people will be able to understand before we go and learn more about how we improve upon it is the PIFO is used today for programmable packet scheduling. So what we do is when a packet is in-queued, we compute a rank for this with a PIFO programmable scheduling. And we'll push this into a priority queue at this rank. And this allows us to implement a large number of different programmable packet scheduling algorithms. There was this interesting work on universal packet scheduling that showed this can emulate any scheduling algorithm. But it has two limitations that we're going to see overcome in this NSDI conference. One is that it requires a significant amount of hardware to implement, in that it requires a large amount of different programmable priorities. We're going to approximate it with a small number of priorities, which reduces the amount of state that is required. We're also going to see that this isn't necessarily fully flexible for all of the programmable scheduling algorithms we want to implement in practice. And so there's a type of programmable scheduling algorithm where you enqueue a packet from traffic class 1, a new packet from traffic class 2 shows up, and we want to update the schedule and the rank for traffic class 1. This isn't possible with a PIFO, and we're going to see work that is able to improve upon it and allow for more expressible packet scheduling algorithms. Okay, so in conclusion, it was hopefully on topic, an interesting discussion that we went over, but the division of labor between our different layers of the networking stack and different protocols. So I think an important area of research, in that I think we'll see a lot of the papers that we will cover over the next 3 days. We'll get into issues related to this. Thank you for having me. Hopefully I didn't go over.
Thank you, Brent. Appreciate that. All right. Prateesh is going to be our next presenter. And which kind of connector do you need?
HDMI.
All right, that's the yellow one. All right, Prateesh Goyal from MIT. And then if you could kind of stand by the podium, I think, then it will get you, I think. Is that right? Yeah, perfect. I mean, I think it's moving, but yeah. Okay, cool. There you go.
Okay. Hi everyone, I am Prateesh. Today I'll give a brief primer on data center networking. I've borrowed a few slides from George. Thanks for that, yeah. In simple terms, a data center is a very large collection of computers within the same geographical location. These computers are interconnected using links and routers. Why do we need to put all these machines in the same location? First and foremost, it's cheaper to house these machines using a common infrastructure. From a networking perspective, co-location implies shorter, inexpensive links. Moreover, if the machines are co-located, then the network latency is very low. The implication is that data centers can support interactive distributed applications where different components of the application need to communicate with each other. Modern data centers are big and are getting even bigger. Data centers can have up to hundreds of thousands of machines, petabytes of storage, and run applications that spread across thousands of servers. This is a simplified schematic diagram of a data center network. At the bottom, we have servers that provide the compute and storage for running applications. These servers are connected to each other using high-capacity links and switches. There are multiple paths between any given pair of servers. Modern data centers boast link capacities of up to 100 gigabits per second, with switches supporting up to 12 terabits per second of throughput in aggregate. So why study data center networking? Data centers are really expensive to build and operate. A substantial portion of this cost is the networking infrastructure. This is a great opportunity for doing research that creates tangible financial impact. Data center is a young and relatively immature field. There are a lot of interesting problems yet to be solved. It's a good area to work in, whether you like applying theory or building real systems. Moreover, data centers are usually run by a single administrative unit, for example, a company. As a result, adoption of new ideas is easier compared to traditional wide area networking. Since data center is such an exciting field, we have 2 sessions in the conference. The first session is from Tuesday, 8:40 a.m. to 10 a.m. The second session is on Wednesday from 4 to 5:20 p.m. I'll now give a brief, give an overview of some of the problems that contemporary research in data center networking deals with. Data centers house a variety of applications. Different applications can have varied performance requirements. Some applications require sub-millisecond level tail latency, while others might require high throughput for data transfer. To achieve these goals, congestion control protocols aim to maintain high utilization for the links while avoiding any queue buildups that degrade latency. Congestion control is particularly challenging in the data center setting. Data center switches have limited buffering, and the traffic demand is bursty and uneven. The combined effect is that a switch can easily run out of buffering and incur packet drops, degrading performance. Moreover, in a bid to reduce latency and save compute cycles, some data center operators have offloaded retransmission of packets to the hardware. This is RDMA that Brent was actually talking about. With hardware offloading, these data centers use primitive strategies for retransmitting the drop packets. As a result, the performance degradation due to drops is even worse. In these settings, congestion control protocols are geared towards minimizing the switch buffering to avoid any losses. Traditional switches only provide support for primitive scheduling policies. So for example, strict priority scheduling or round robin. With these switches, a network operator can change the parameters of the scheduling policy, but they cannot change the scheduling algorithm itself. Recently, with the advent of programmable switches, there has been a push for supporting programmable packet scheduling in switches. With programmable scheduling, the network operator can customize the scheduling policy based on the requirement of the application. So for example, to minimize flow completion times, a network operator can deploy shortest remaining processing time. For programmable scheduling, we want a design that is capable of supporting a large number of flows. Another important challenge is that switches have very stringent resource constraints. Switches have a limited memory. This implies we can only maintain a small amount of state. Moreover, switches only have a few cycles to process a packet. If the operations for scheduling take a larger number of cycles, then the switch pipeline will stall, wasting valuable link bandwidth. Network measurements are helpful to discover bugs in the network and gain insights for designing better networking systems. So for example, learning where congestion happens in the data center can be helpful in designing a better congestion control protocol or a new routing policy. The challenge here is to gather these measurements at a fine-grained precision for them to be useful. Moreover, gathering these measurements should not hurt performance. That is, measurements should not increase packet delays or slow down the switch. Most data centers today use electronic switches and have a fixed topology. Recall that bandwidth demands in data centers can be bursty and uneven. Traffic bursts can cause congestion in a part of the network and hurt latency of competing flows. To solve this, data center operators often over-provision bandwidth. Over-provisioning is good for reducing latency and increasing throughput, but it wastes resources. Recently, there have been proposals for optical data center interconnects. With optical interconnects, it is now possible to reconfigure the data center topology or a part of it over a short time. With reconfiguration, we can dynamically direct the capacity of the network to where the demand is. As a result, we don't need to over-provision the network as much. The challenge is when and how to reconfigure the network. While reconfiguration times are small, too many reconfigurations can hurt both the throughput and the latency, as we cannot send traffic on part of the network that is being reconfigured. Additionally, it is very hard to decide what is the right reconfiguration topology for the current application demands. Most data center topologies have multiple paths between a given source and destination pair. We can leverage these multiple paths for routing the packets or flows to uniformly distribute the traffic load in the network. This spreads and reduces the congestion at the tail. That's it. Please come and attend the technical sessions to learn more about data center networking. Thank you.
All right, thank you very much. Next up, we're going to be covering operating system, storage, and hardware with Amy Ousterhout. Are you also HDMI? Or we have USB-C?
Yes.
Okay, that would be this one. And then that is number 4. Excellent, okay.
Thank you. So hi, I'm Amy. I'm a postdoc at Berkeley, and today I'm going to talk about the OS storage and hardware session. So this session has 6 different papers, and we can sort of broadly categorize these papers based on what environment they apply to. So the first paper, XL-TCP, applies in the data center and also in the wide area. The next 3 apply in the data center. NetTLP is for prototyping, so you can think of it as applying in the lab. And then Pando applies across the wide area. So I'm going to start by talking about the first 4 papers together because they all have sort of similar motivations because they all apply to the data center. And then I'll talk about the last 2 a little bit separately. So there are a couple of big trends that have been impacting data centers in recent years. One of these trends is that we have faster networking and storage devices. So for example, if we look at NICs, in recent years we've had NICs emerge that have latencies of a couple of microseconds and throughputs of 100 gigabits per second or even higher. Higher speed NICs are on the way. On the storage side, we also have much faster flash devices. So we have flash devices with latencies of about 10 microseconds, and they can support throughputs of up to about 500,000 I/O operations per second. And both of these are about an order of magnitude faster than, say, what we had available to us about a decade ago. Another major trend that's impacting data centers today is increased demand for memory. So we see the rise of applications like big data applications, which perform computations over large amounts of data. So they need all this data to be present in memory at once. And this yields increased demands for memory. A third trend that's impacting data centers today is the slowing of Moore's law. So in the past, we would get new, faster CPUs available every couple of years. But as Moore's law slows, this is no longer true. This means that it becomes more and more difficult to increase the compute capabilities of an individual CPU. This puts increased pressure on data center operators to find ways to use their CPU cycles more efficiently. So you want to be able to spend as many cycles as you can performing useful application-level work, as opposed to sitting idle or wasting time processing packets or handling storage operations. In response to this third trend in particular, we've seen the rise of Smartnics. So these have emerged to help address the challenge of CPU efficiency. And the way that they do this is they help reduce the amount of CPU cycles that you spend processing packets by allowing you to offload some functionality to a Smartnic. And overall, there are sort of 3 main categories of Smartnics that have emerged so far. The first is ASIC-based Smartnics. So with these, there's some limited amount of functionality that you can program on an ASIC chip that's on the NIC. So these offer very high performance, but there's a very limited set of operations that you can actually program. So simple functionalities like encapsulation or decapsulation or header rewriting. Another class of Smartnic is FPGA-based Smartnics. So with these, you put a programmable FPGA on your NIC. These have high performance and very high flexibility as well, but they can be very difficult to program because you often have to utilize a pretty low-level language like Verilog when you're programming the FPGA. And finally, we have SOC-based Smartnics. So these typically have many cores running on the NIC, so usually, say, dozens of cores. And they're typically wimpy cores, so they run a little bit slower than the cores you would have on your end host. Because these are just regular cores, you can run a regular operating system on them if you want. So the programming is typically a lot easier than with the other Smartnics, but they do have lower performance. So the first two papers in this session focus on Smartnics and how you can use them in order to offload packet processing to the NIC. So the first of these is XL-TCP, which focuses on offloading connection management. So they look at sort of two main classes of problems, short-lived connections and L7 proxies. So when I say short-lived connections, I mean, say you have a client that's communicating with a server, and every time the client wants to interact with the server, it'll open up a connection, send a request, get a response, close the connection. And it'll repeat this for every time it interacts with the server instead of reusing the same connection. And when I say an L7 proxy, you can think of a load balancer. So you have an HTTP request that goes to this load balancer. It looks at the request and then makes a decision about where that request should be sent to, and then passes it along to another server in order to actually handle the request. And in both of these settings, we can see that you're creating and destroying a lot of connections and managing a lot of connection state. So what the authors point out here is that you have very significant overheads from managing connections and just relaying packets in these scenarios. So what they do with this paper is that they offload this functionality of specifically managing connections to an SOC-based Smartnic. The next paper in this session is Tonic, and so they also focus on making things efficient by offloading functionality to the NIC, but they add an extra goal of programmability. So they want it to make it possible for users to come up with new congestion control protocols and implement them so that they can run at line rate on the NIC. But they want to make it easier so that you don't actually have to spend a ton of effort trying to program just the basic NIC functionality, and you can really just focus on the congestion control functionality. So their focus is on enabling you to offload specifically transport logic to the NIC. And they sort of separate this into two decisions. The first is what they call data delivery, so which data should be sent next. And then the second is congestion control, which is when should that data be able to be sent. And what Tonic does is it provides a programmable architecture that makes it easier for you to offload this transport logic to an FPGA-based Smartnic. So their goal is to sort of handle all of the complexities of actually programming the FPGA and allow you to write your data delivery and your congestion control in sort of a pluggable module that just fits in nicely with all the other pieces that they've implemented. So now let's talk more about some of the new memory and storage devices that are emerging in order to handle these workloads that demand more and more data. One such device is NVMe. So you can think of this as persistent memory. It's like regular memory, but it's persistent. So if your server crashes, when you reboot it, all of your data will still be present in memory. So it sort of merges memory and storage, so you don't have to maintain these separately anymore. And one of the things to note about NVMe is that it's byte addressable. So you can actually access it the way you would access normal memory using normal load and store instructions. Another thing that's important to note is that it has latencies on the order of about 100 nanoseconds. So this is slower than DRAM, but it's not an order of magnitude slower than DRAM. And to date, I think there's only actually one vendor that makes NVMe, and it's Intel and their Optane DC persistent memory. So this is actually like a very recently emerging technology. Another recently emerging technology is NVMe devices. So NVMe is actually an interface that's widely used by many new faster storage devices, such as SSDs. And these, unlike NVMe, that's actually block addressable. So if you want to interact with the device, you have to read a whole block of data in, then modify your block of data, and then if you wanted to persist it, you have to write out the whole block to your device again. And these devices have latencies on the order of 10 microseconds, which is much faster than storage devices of the past, but not as fast as NVMe. And the question that the two papers in this session that focus on memory and storage ask is, can we efficiently access these devices over the network? Why would you want to do that? Well, if you actually attach your device to the network, then it can be shared by many different clients, as opposed to only being accessed by the one server that it's attached to. So it allows for you to use these devices more efficiently. So the first of these talks is FileMR, and their goal is to enable low latency and efficiency when you're accessing NVMe over the network. So they want to leverage RDMA, which, as has been described before, allows you to access remote memory on another server without invoking the remote CPU. And one of the things to note about RDMA is that the abstraction it uses for managing memory is memory regions. In contrast, the abstraction that NVMe uses to manage memory is files. And so what the authors of this paper observe is that if you try and just naively combine these two technologies together, it's actually really inefficient and redundant because these two technologies use a different abstraction for how they access memory. So there's a lot of functionality like naming, access control, memory allocation, et cetera, that is duplicated between these two different systems. So what they do is they propose a new abstraction, which they call file MR, which allows RDMA connections to be backed by files instead of by memory regions, as in the past. The next paper in the session is I-10, and I-10 looks at the problem of accessing NVMe devices over the network. So they say if you want to access NVMe over the network using TCP, you get really poor performance. Alternatively, you could access NVMe over the network using RDMA or a user-space network stack. The problem with RDMA is that this requires that you have RDMA network infrastructure already. And the problem with user-space network stacks is that these typically require that you modify your application in some way in order to take advantage of them. So the question they ask in this paper is, can we achieve good performance with a fully in-kernel approach? So can we get performance similar to using RDMA or a user-space network stack, but implement it entirely in the Linux kernel? So the next talk in the session, we leave the data center, and it's called NetTLP, and it focuses on PCIe devices. So the first question you might ask is, what is PCIe? PCIe is an interconnect that allows devices on a machine, such as a GPU or a NIC or an accelerator, to interact with your CPU or memory or with each other. So basically, all the parts in this figure that are in blue are PCIe. And so the authors in this paper observe that if you want to prototype new devices, new PCIe devices, this can be really challenging. And it's also really challenging to observe the behavior of PCIe devices and to debug them. Unfortunately, existing approaches to addressing these challenges are either entirely in hardware or entirely in software. So what I mean by that is that one way you could prototype a new device would be to implement it entirely in software and then emulate all of the different components of PCIe in software. But unfortunately, this approach has some inaccuracies. At the other extreme, you could prototype your new PCIe device using an FPGA and then test it with the real hardware PCIe components. But as I mentioned before, programming FPGAs is quite challenging. So this isn't really an easy or convenient prototyping environment. So what the NetTLP authors do is they introduce this prototyping platform. So basically, they let you prototype your device in software. So you can write your new PCIe device entirely in software, and then they provide a mechanism for interfacing with the actual PCIe hardware so that you can test it and debug it and observe it interacting with real PCIe devices. Then finally, the last paper in the session is called Pando, and they look at trade-offs in geo-distributed storage. So for example, if you run an application that's globally distributed, your users are globally distributed, your data is globally distributed, you have to make choices about where to store your data. And typically, you're facing a lot of different competing goals. So one goal is you want low latency. Both you want users to be able to read your data with low latency, but you also want them to be able to write it with low latency. You also want to achieve low cost for yourself. You don't want to pay extra storage costs to store your data in more places than is necessary. You also want strong consistency so that when a user reads data in one location, they see the writes that were written by a user in another place in the world. And finally, you want fault tolerance so that if any of your data centers go down, you still are able to reconstruct your data. And so what the authors of this paper point out is that existing approaches are very far from optimal. So ePaxos is one of the state-of-the-art replication protocols in this space, and they say it is far from optimal. Unfortunately, I don't have enough time to give you a background on ePaxos in this session. And so what the authors do here is they improve on the status quo by considering the latency between data centers, and they leverage this information in order to create replication protocols that better optimize for these different trade-offs. So to summarize, there's 6 different papers in this session that talk about the data center, prototyping, and the wide area, and I encourage you to attend the session to learn more.
All right, excellent. Thank you so much, Amy. So the next session is going to be on monitoring and diagnosis from Behnaz Arzani from Microsoft. HDMI, okay, that's this guy.
Okay, hi everybody. Today I'm going to be talking about diagnosis and monitoring, and my goal is to first talk about why do we still find diagnosis and monitoring hard and important, and then talk a little bit about existing work in this space. The talks are going to be distributed across multiple sessions, so I'm not going to go into the details of the individual papers. But if you are like me, when you started undergrad, you would think this is what a network typically looks like. Like, this is my view of what a network looked like when I started my undergraduate school. Incidentally, this particular network is YARPANET in December of 1969. And what happened over time is that our network started to get bigger, where we moved to the internet, and the internet in 2004 had over 1 million nodes. And then we moved to data centers. And now data centers themselves are almost as big as the internet was in 2004. And what's hard about this is that these networks have become more and more complex. Now, I'll start with the data center network as an example. But while the data center network topology is very, very simple, it's actually not that simple. We start with adding virtualization for our servers. We have storage clusters that manage the storage for many of these VMs. Add on top of that logical components like load balancers, virtual switches that manage how our traffic gets routed, different protocols that are running, like BGP on our switches, TCP and UDP running on our servers, and monitoring infrastructure. We have things like SNMP and monitoring agents that are running on our every single server in these data centers. And you can almost see why managing and monitoring and then diagnosing such a system would be hard. And the goal of diagnosis is really to track problems that happen in these networks, to figure out what went wrong, and for monitoring to basically tell us when something is wrong so that we can quickly react to it. Now, this is a hard problem because when something breaks, we might see the symptom here, but really this switch or any of the other switches or load balancers or any of the other network components could be really at fault. And so if we don't have effective monitoring infrastructure and effective diagnosis systems, it's going to be really, really hard to pinpoint what actually went wrong and how it went wrong. There are a lot of moving parts to this system. Every single of these components can change because they are managed by different teams, and these teams often update them asynchronously. It's almost impossible to get an accurate snapshot of the end-to-end systems. There have been some papers on how to do this, but a lot of them are really, really hard to implement in practice. And it's hard to distinguish a lot of the times the cause from the effect. It's hard to figure out whether what we're observing is actually the symptom or is the actual root cause of the problem. And meanwhile, customers are unhappy when this happens. And there's a really funny example of this when Facebook broke and people started to call 911. So this is how much we as customers actually care about our networks breaking. And the reason it's important to get monitoring right is that we're not just talking about, oh, my link completely failed and it's not working anymore, right? We're talking about things that can be gray failures, things like software bugs. Even things like VM compromise require sometimes for us to monitor the network to be able to detect them. Configuration errors are another example. Intermittent packet drops or on a bad link are another. And so when we talk about diagnosis, let's talk a little bit about what operators do to be able to do diagnosis. The first thing is we need to figure out something is wrong, right? So there's monitoring infrastructure that we deploy to be able to know that something is not working in our network. And sometimes like these monitoring systems can fail, and so in those cases, customers might report that a problem happened. Then we need to find who's the right expert to call to help us figure out what went wrong and how it went wrong. And then finally, these experts investigate, look at the monitoring infrastructure they have to try to understand the root cause and fix the problem. And so the works that you see in networking diagnosis and monitoring have to do with these three basic areas of the diagnosis process. So there's many works, for example, on monitoring and net reporting, and what they try to do is balance the load on the network infrastructure that they impose versus the visibility that they give us in terms of what is happening inside the network. So for example, if you think about works that have happened in this space, there's things like ping mesh that look at end-to-end latency in the data center setting to tell us whether there's connectivity in the network even, to Blink, which actually falls into a number of different categories, but basically monitors the effectiveness of links at routing traffic. And then there's also Marple, which again provides a way of implementing effective monitoring in hardware inside the network. We also have to find who is the right team when we're trying to figure out, to blame when we were trying to diagnose the network, because a lot of the times what happens is that the different components of our infrastructure are managed by various different teams, and so it's important to get the incidents that happen to the right expert as quickly as possible. So works such as NetPro and DeepView deal with this problem of trying to figure out who is responsible when a problem happens. And then the last hop is actually doing the diagnosis. And this is an extremely difficult problem historically. And that's why throughout the years, we've had many, many, many different works. And this is just a subset of the work that people have done in this space. Things that go from tomography-based approaches, which try to triangulate where the problem happened and how it happened, to Sherlock and NetMedic, which use probabilistic methods to do so, to PathDump that provides an abstractions for operators to implement their queries about what does the monitoring systems underneath tell us about what is happening and where the problem is happening. And so with that, I'm going to end a little bit early.
All right, thank you, Behnaz. All right, we've got Robert Beverly from the Naval Postgraduate School, just down the coast a bit. And then what kind of adapter do you need? Perfect, it's all set up right here. Awesome. Thanks. Okay, great. All right. Okay, thank you.
All right, thanks. So, hi, my name's Rob Beverly, and I'm here today to give you a primer on internet measurement. And one of the things that you'll find if you go to a cocktail party and you tell people that you measure the internet, they sort of look at you with bewilderment, like, you measure the internet? Like, what does that even mean, right? And so, we all know that the internet is pervasive and crucial to society, but there's a few things that make it a bit more complicated. First of all, it's constantly evolving, whether that means how it's used, what applications are on it, what protocols, what structure it has. In combination, it's distributed and it's multi-party and it's economically driven. And finally, it has this massive scale, and there's lots of abstraction that comes with this massive scale and lots of information hiding that comes with that. And so as a result of these sort of constraints, there's a lot of fundamental questions that we just have no real good answer to. Things as simple as like, well, how many hosts are there on the internet? Or where is there congestion in the network? Or something like, is this packet legitimate or is it spoofed? Or why can't I reach a website? Or what is the topology of the internet, right? So these are sort of basic questions that have been around for a long time that we still don't have a great answer for. And so there's lots we don't understand, and this makes it sort of a natural fit for experimental science. So why are we doing this internet measurement? Some of the previous primers before me talked about using network measurement for various tasks. First of all, it informs our internet evolution. So we have this cycle of deploying everything from applications to topology to whatever, and then seeing how it goes, right? So whether that's IPv6 or Dash or QUIC or DNSSEC or whatever the app du jour is, we often want to measure how it's doing. We also want to make the internet better. So this might mean security, or it might mean resilience, or accountability, or privacy. We also want to inform policy. So we might be interested in how we get access for everyone, how we do freedom of network, or how we do network neutrality. And then, of course, many times we do measurement simply from some sort of business or economic motivation underlying it. As an example of this, often companies will try to measure things to improve performance, either to get better user experience and or more time for the back-end processing, which in the end equates to more revenue for those companies. So what are some of the hurdles that the community faces today when trying to do network measurement? Well, I alluded to scale. There's lots to measure. Access is hard to get. These things were not designed to be measured. The protocols, and often the providers are actively trying to prevent you from measuring them. And ground truth is elusive, right? It's very hard to validate the measurements that you might make if you're trying to do this from outside of the network. And then finally is the problem of reproducibility. So in our community, unfortunately, the best data and results are often sort of hoarded, whether that's for private, because they're mired in privacy concerns, PII, things like that, or it could simply be because of self-serving reasons. But I don't want this to be like a completely negative talk, and indeed there's been lots of progress, right? So despite these hurdles, there's been lots of successes. For instance, we have a better idea of the network topology than we ever have had before. There's been many measurements that have driven protocol improvements and made life better. There's been measurements that have driven security, everything from DNS to securing the routing system. And today there's a variety of measurement platforms, both active and passive, available to try to get introspection into what's going on. And then finally, reproducibility and artifacts have become more and more emphasized within our community. As one example of this, I was recently involved in the ACM Internet Measurement Conference, where we explicitly tried to incentivize folks to do reproducibility studies by fast-tracking some of these papers, some of the submissions to a CCR that was focused on reproducibility and artifacts. So this is something that the community is making progress on. So George also asked me to give an overview of some of the techniques that we use in this space. So there's a variety of techniques. I've come up with one taxonomy. There's many different taxonomies, but this is one way that you might think about the different techniques in internet measurement. I've divided it into 3 dimensions: the data plane, the control plane, and what I'm going to call layer 8. So in the control plane, we have passive techniques. One of the things that's given the community lots and lots of insight and power has been this notion of looking glasses, right? So looking glasses are just points in the network where we can view things like the routing tables, right? But not only can we view them in real time and see what's happening, we can also get historic snapshots of the routing tables and even the individual update messages. And we can get this from hundreds of different vantage points, because where you measure from, of course, will change what you see. In the active space, we also have platforms such as peering, which have allowed us to do really cool things, where now, as researchers, we can actually actively experiment with the routing system, participate in it, and understand how a different approach to doing something impacts the system. And there's been a bunch of papers that have come out of this sort of approach of analyzing the control plane. I've thrown up a few of these, but in the end, the impact has been that we've been able to get a better sense of the reliability of the network, the security of the network, and the performance of the network. In another dimension, data plane techniques, again, can be divided into both active and passive techniques. So at the data plane, some active techniques, so things like high-speed, exhaustive probing of the entire IPv4 internet is now common. This was something that was sort of unheard of a few years ago. We have platforms now that allow us to do active measurements, again, from many, many different vantage points. Things like ARC and Atlas and scans.io and Planet Lab, even though it's mostly dead, but it has had a big impact, right? And so again, these systems that I've mentioned, many of them spend their entire lives doing nothing but performing measurements on the data plane. And they perform these measurements and they archive them. And this gives us another source of rich historical data from which to draw. On the passive side, a very common thing that's used today are network telescopes. Network telescopes are basically the idea to capture a bunch of hosts, to set up a network with no hosts and capture all the packets, right? So intuitively, this sounds weird because you would say, okay, if I set up a network with no hosts, nothing's going to show up. But that's sort of the whole idea here, right? Which is that with no hosts, what you're going to see is all of the backscatter, the scans, and the misconfiguration traffic, which gives us a bunch of security insights. And again, I'm emphasizing this many times, but these systems also run continuously. They capture all of the packets, and they are archiving them. And they're doing this from very large vantage points, things that are on the order of a /8 or 1/256th of the internet. And a bunch of papers have come out of this. Again, I've just thrown up a few that I thought were important, but some of the insights that we've been able to get from this are things like understanding emergent events, right? Understanding policies and changes, and understanding attacks and defenses in the internet. In the next dimension of my taxonomy would be techniques that are at layer 8. And I feel sort of compelled to put this up here. So we talked about more technical approaches, but I mentioned that getting data is often one of the biggest obstacles to performing some of this research, right? So many of the data sources that we get are from different kinds of collaborations, either with industry, colleagues, partnerships, universities. Folks are having lots of success doing various kinds of crowdsourcing. And there's even things like data exchanges, things like SIE and DNSDB that are having good success. And then ground truth and validation is another technique that is crucial and a big problem that we have in our community. But I've been sort of amazed over the years of how much actual validation you can get if you just ask. What comes with that, of course, is knowing the right people to ask, but not entirely, right? So, for instance, in some of our own work, we've posted things to mailing lists, just things like Nanog, which is a mailing list for network operators, and you'll be amazed who responds and gives you insights and gives you various kinds of validation, ground truth, and insight that you really didn't have before. You can also get ground truth and validation from research and engineering networks and other places or relationships with providers. And there's been a bunch of papers, again, using these sort of layer 8 techniques to get insights. And the result is that we've had to sort of come up with creative ways to obtain better data, but our standards of validation have been raised, and the realism and real-world impact has also been raised as a result of trying to pay attention to this layer 8. And then, of course, I mentioned these three techniques, but they're almost never used in isolation, right? And so most research that you'll see in the space of internet measurement uses multiple of these techniques. So a big use of this data is really in data fusion to get sort of deeper insight and more validation. And then, of course, there's this huge value in the continuous and archived measurements, right? This gives us this ability to have retroactive understanding of an important event. So this is this whole idea of let's instrument the network, let's have it capturing everything that we want to, and then when something really important happens, we can go back and analyze that data in much more detail. And there's lots and lots of examples of doing this. A few thoughts before I wrap up here. So, measurements underlie systems and science. Internet measurement is hard, but I definitely don't want to give you the sense that there's not progress being made, because the community is extremely active. And I guess I would encourage folks to think about the measurement input and output in your own work, right? When I talk about input, I mean it's often easy to sort of not question the quality of the input data that you have. You just I need this data, someone give it to me, right? And that's extremely dangerous in this space. There is data that's not always good. I think it's also important to be skeptical of closed measurements. There's many papers that say, just believe us, we measured it, right? And that's probably something that we don't always want. There's a great paper, if you haven't read it, it's now sort of a classic paper by Vern Paxson from 2004 called Strategies for Sound Internet Measurement. And something that's really nice in this paper, well, there's many things that are nice in this paper, but you really want to be sure that what you're measuring is what you think you're measuring, and often it's not. And Vern runs through some really great examples of how you can run afoul of this sort of misconception. And also, in your own work, think about what new measurement techniques you can leverage, and also think about contributing output measurement data and code and artifacts to the public, because we really need these sort of canonical data sets for doing reproducible science in internet measurement. And that's all I have.
All right, thanks, Rob. What's that? USB-C, okay, great. So Raluca out of Popa will be our final speaker for tonight. And there's the right cable, I believe. Speaking today about security. And with that, I will turn it over to you.
Thank you. All right, so welcome to the last session of the preview session, the security session. There will be 6 very interesting security talks on Thursday, and they all have in common one theme: the servers or clouds can get compromised. So why? Well, as you hear in the news, the problem continues. There are massive cloud attacks. So the numbers always grow larger and larger in terms of the data breaches. Second, there could be curious or malicious cloud employees, even when the cloud provider is actually well-intended. And finally, government subpoenas could extract data from different clouds. So in the session, the works take 2 approaches. One approach is to prevent the attacker from seeing data. So once the attacker actually broke in, to prevent the attacker from seeing the data or modifying the data. The other approach is assuming that the attacker broke in and managed to actually change data, maybe insert code, maybe change the control. How do you detect which parts of the system were compromised? So in terms of preventing the attacker from seeing the data or modifying the data undetectably, there's 2 approaches. One is via cryptography, and the other is via hardware enclaves. So in terms of cryptography, we have systems such as XRD for messaging, then Ghost Stories for storage, TimeCrypt is for time series databases, and Spider is for payment networks on blockchain. The second approach is via hardware enclave, so this is via trusted hardware execution, and this is, for example, Telekin for GPU-based systems. And in the final approach, to detect when the attacker after the attacker broke in, to see what VMs got compromised, the system private eye will basically provide a system for detecting which cloud VMs were potentially compromised. So I won't be able to give you a lot of background into each one of these, but instead what I'll try to do is to provide a context at a high level within which each one of these works contributes, so hopefully you can appreciate each work better. So let me start with a cryptographic approach to basically building systems and preventing the attacker from seeing or modifying data. And a very basic pillar here is understanding the notion of end-to-end encryption. So traditionally, people think of encryption at rest, which is only the storage is encrypted, or encryption in transit, which is only the network being secured. But end-to-end encryption covers the whole progression from user to cloud and back to user. Basically, a user has a key on their device, and the cloud never receives the key, encrypts some file or message, sends it encrypted to the cloud, And then the cloud sends this file back to some user who can actually decrypt and obtain the data, but also can verify whether it was not tampered with at the compromised cloud. And there's been a lot of work in end-to-end encryption, both in academia and industry. In fact, in industry, there has been more and more adoption, which is very exciting. For example, WhatsApp brought end-to-end encryption to 1.5 billion users. While end-to-end encryption is great, it's not enough. There's still leakage, and in particular, the two works, XRD and GhostStore, in the security session, explore metadata leakage. So end-to-end encryption protects the content of a file or of a message, but it doesn't protect metadata. So, for example, you can see who, if you're compromising the server, you can see who talks to whom, or you can see who shares a file with whom, or who reads or writes a file. For example, if Alice is communicating with her doctor oncologist using WhatsApp, then the WhatsApp servers can see that Alice and doctor oncologist are talking with each other, so maybe she has cancer. Similarly, if Alice's medical file is accessed regularly by a doctor oncologist, again, a compromised server could infer that Alice suffers from maybe cancer. So that's why it's very important to protect against metadata, not just protecting the file content or the message content. And the two papers, XRD and GhostStore, in the security session are going to talk about how to hide metadata for messaging and for storage. And there's been a line of work within each of these areas, but the main difficulty has been achieving scalability and low overhead. And this is where these two works make a significant progress. The works also look at the integrity side of the problem, namely, what if a compromised server changes data or messages? For example, the server could corrupt a message or a file, or could provide inconsistent views of the same file to different users, or it can roll back a file. And both XRD and GhostStore prevent active attacks by the server by enabling clients to detect when certain violation happened. And again, similar challenges that they had to overcome is scalability and overhead. So, but messaging are actually, they move data around, but how about computing on that data? And TimeCrypt looks at querying time series data. So let's go back to the end-to-end encryption diagram. How will the cloud compute on the data now that it's encrypted? With end-to-end encryption, the cloud never gets the decryption key, so it can't actually decrypt the data to compute on it. So how can it do this computation on encrypted data? So the idea of computing on encrypted data is a useful paradigm introduced in 1978 by Rivest, Adelman, and Dertouzas. It sounds very magic, but basically here's the idea. So the data is encrypted in the cloud, and the user has a decryption key. The cloud doesn't have the key. Then the user sends a function to the cloud, say, hey, please run this function for me. The cloud executes this function directly on the encrypted data without decrypting the data. Okay, so this runs on the encrypted data by leveraging special properties of the encryption scheme. And then the result, which is again encrypted, is returned to the user who can decrypt and obtain the function of the data. And this paradigm is super, super useful because the cloud can still do the work and compute the function, but without actually seeing the data. And this always sounds magical, and how can you possibly compute on data you cannot see? So to just help you build some intuition, I have an example here that I find that helps people, get more of a sense of what's going on. So let's consider that our function f is a simple addition. Then take the PCIe crypto system, which is an encryption scheme that basically enables computations like addition. So the way the PCIe encryption scheme looks like is the encryption of x is some big number g to the power of x, and then times some randomness to the power of n modulo n squared. Similarly, the encryption of y is g to the y Again, some other randomness to the power of n, modulo n squared. So now the server has encryption of x and encryption of y, and has no idea what values they're encrypting, but it can multiply them. And if it multiplies them, you can see what happens in the exponent of g. X adds with y, and then the randomness bundles together. So essentially, we get an encryption of x plus y. So you can see how the server was able to basically compute this addition underneath encryption. It wasn't able to see what x was or what y was, but it was able to multiply them and thus obtain the encryption of the sum. And besides this simple addition, there's actually, you can implement any function you want with fully homomorphic encryption. The problem, though, is performance. There's been a ton of progress done in that space, but it's still orders of magnitude slower than regular computation. So instead, systems like TimeCrypt take a different approach, and the approach is to build a practical system is you focus on a specific workload. And you extract what are the core operations in that workload, and then you tailor cryptographic primitives to those core operations so that they can be fast. So the crypto can't do every function, but it can do specific operations very efficiently. For example, Payet, the one I just showed you, could do addition efficiently. It's a multiplication. Okay, and then you develop system mechanisms such as planner or other things to compose them. And there's been a long line of work in this space initiated by CryptDB. Now, the TimeCrypt system that you're going to hear about on Thursday is able to query time series data while enforcing access control. So for example, it can do operations such as aggregates over encrypted data in a certain time range very efficiently, and can also ensure that users can only query parts of the data that they have access to and enforce that cryptographically as opposed to using a trusted party. All right? So now we're going to go to Spider, which is slightly different than these three works. It focuses mostly on integrity of payment networks on a blockchain as opposed to confidentiality, and in particular making those payment networks efficient. So to understand Spider, I think an important piece of background is to understand what payment channels on a blockchain are. I assume you all know what blockchains are at a high level, but really one of the main parts of the blockchain that you need to know about is that every operation has to be signed. So whenever Alice wants to transfer some balance to Bob, she has to sign that she's really intending this before placing it on the blockchain. So there's a cryptographic enforcement of her intention. Now, what payment channels try to get at is the fact that blockchains are high latency and have low throughput. So, for example, if Alice and Bob want to do many transactions very efficiently at high throughput, ideally they should be able to do that between the two of them without incurring the low throughput of the blockchain and the high latency. But they still want to do it in a secure way because they don't quite trust each other. So payment channel enables them to do exactly that. Alice can open a channel by just placing a record on the blockchain saying Alice opens a channel to Bob for, let's say, up to 10 bitcoins. So she can lose up to 10 bitcoins to Bob or spend that much with Bob, but no more than that. Then the nice thing is that Alice and Bob can perform transactions with each other, directly with each other, at high throughput, outside of the chain, off the chain. They exchange to each other signatures saying, okay, I'm giving you, Alice says to Bob, I'm giving you 2 bitcoins now, and Alice signs. But all these signatures don't have to show up on the blockchain. At the end, they can close the channel by putting the final state, which is signed by both of them. For example, Alice has 2 bitcoins and Bob has 8 bitcoins. So for example, she gave to Bob overall, she gave him 8 bitcoins, but then she still has 2 bitcoins left as part of that channel. So the really cool thing about payment channels is that you can make this transfers between Alice and Bob at really, really high throughput off the chain, but only put on the chain 2 transactions, the opening and the closing of the channel. Okay, so what does this have to do with networks? Well, you can actually have multiple users who have payment channels between them. So that's a network of payment channels. And the nice thing is that right now, if Chris and Dan want to transact with each other at high throughput, they don't need to necessarily open a new payment channel because that's high overhead. They can instead use the network of payment channels. And this is currently deployed, for example, in Bitcoin using the Lightning Network, which routes based on the shortest path. So this gets us to the problem that Spider is trying to solve, that this routing is not necessarily the best. So it still affects the throughput, right? The throughput could be much higher if, for example, the routing would take into account balances. For example, there are issues with transactions with a high amount, high budget. If those get routed over links that don't have that much budget left, then they fail. Or if some transactions deplete certain paths of payment channels, then one needs to do expensive off-chain operations, on-chain operations. So Spider is basically trying to provide much higher throughput by designing routing with balances in mind. Okay, and they have a variety of techniques that really exploit knowledge of the balance to improve throughput. All right, so these were the mechanisms that protect against a server being compromised via cryptography. The other type of protection is via hardware enclaves, which are basically pieces of trusted hardware. Telekin is protecting, secrecy of data and of systems for GPU-based systems. So let me give you a bit of background into enclaves, CPU enclaves and then GPU enclaves that would be useful when attending the session. So CPU hardware enclaves such as Intel SGX are a hardware-enforced isolated execution environment. The idea is that on the die you have an extra module, the MEE, which has keys for encrypting the data when it goes to memory and decrypting it when it comes back from memory. The data is only decrypted inside the processor, and outside of the processor it's always encrypted. So even if an attacker compromised the operating system or the whole software stack, the attacker only gets to see encrypted data. And these are not just academic systems, and these are actually used in industry. For example, there are cloud offerings such as Azure Confidential Computing and Alibaba Cloud. A very important piece of very important technique with hardware enclaves is remote attestation. The idea is that a client can attest what code is running in an enclave and establish a secure channel with that enclave. For example, let's say that the client has some client code. They can send it and initiate an enclave using that client code. Then the enclave has a mechanism called measurement, which is able to essentially hash the client code and send an attested hash, basically saying, yes, this hash is running, code is running inside the enclave, and the enclave itself is certified by the vendor, let's say by Intel. The client can check the hash, and if it's happy with it, then it can establish a secure channel with the enclave by using the public key that was certified as part of the response from the enclave. And in that secure channel, it can then share a symmetric key. Once you have a symmetric key, you are able to send from the client to the server encrypted code or data, and then keep interacting with this enclave in a secure way. So GPU enclaves, for example, the Graviton work, extend essentially the CPU enclave to the GPU. They provide hardware primitives in the GPU for remote attestation, similar to the CPU, and the remote attestation can be used to establish a secure channel between the CPU enclave and the GPU enclave. Also for context isolation, such as isolating code and data from other processes in the system, and secure command submission to prevent, for example, malicious commands from being sent to the GPU by the attacker. And the guarantees it aims to provide are very similar to CPU enclaves, code and data secrecy, integrity of execution and data, and the remote attestation. But one big problem with enclaves are side channels. And there's lots of different side channels: cache timing attacks, branch predictor-based attacks, page fault attacks, memory bus-based attacks, speculative-based execution, and other timing attacks, and so forth. But the one thing to notice is that a lot of these attacks, the first 4 here, reduce to exploiting memory addresses. Enclaves don't encrypt which memory address they're fetching from memory. The data is encrypted in memory, but when you go and get something from an address, that address is not encrypted. So the attacker can extract it in various ways, either through cache timing, by seeing which addresses are loaded in the cache, or through the branch predictor, or from the memory bus, in various ways. And if these addresses depend on secret data, then they can leak secret data. And there's been a long line of work on CPU enclaves to protect against these side channel attacks, either via so-called oblivious algorithms that make the same, make a predefined schedule of accesses to data, or via cache partitioning, or via many other mechanisms. The Telekin work focuses on side channels on the GPU enclave, especially in the interface between the CPU and the GPU enclave and their secure communication, and protects against timing side channels on that interface. All right, so this class of work was aiming to prevent the attacker from stealing data or code, or modifying data or code. But now, private eye comes essentially after the fact. So consider a cloud where you have many VMs. The question is, how can you detect which one of those VMs was compromised? And that's a very, very hard problem. Currently, a lot of cloud providers, for example, Azure, offer something called OBDs. So these are basically introspection-based detectors. They are monitoring agents that if you enable them in a VM, then they monitor the process execution, the binaries, the VM logins, and they even use machine learning to detect various attacks. Now, the problem with these OBDs is that they don't scale well. They're very heavy. There's a lot of monitoring and logging happening. But they also affect privacy because they're monitoring what's happening inside your VM, including VM logins. So if you look at the numbers on Azure, there's only 5% of the VMs in Azure that use OBDs due to these issues. Okay? So the question is, with only this many OBDs, how can you actually detect there's various attacks happening and which VMs are compromised? And how can you detect how can you provide a method that does not affect privacy? So Private Eye provides a scalable and more private monitoring by basically inspecting the flow patterns. So the paper argues that flow patterns in many situations can point to anomalous behavior such as attacks. So if a flow pattern changes from one situation to another, it could point to an actual attack. So the paper basically is able to monitor these flow patterns and detect in which cases there's, which VMs are compromised. All right, so this was the overview of the security session. There's 6 very interesting works that I think are making significant progress in system security. So I hope to see you at the session.
All right, thank you, Raluca. And thanks to all of our speakers. Let's just do one round of applause for everyone who was able to give the preview talk. I appreciate that. Great, so that is the preview of the next 3 days. We have 65 amazing talks coming up on a range of topics, and so we're very excited to see all of you starting tomorrow morning. All right, thanks so much.